after I clicked record. Okay, I'm clicking record, and now I'm going to re-say what I just said, which is that I extended the due date for exam 2 through Sunday. So it's not due Friday, it is now due Sunday, which is, I posted it in an announcement, and I changed the assignment due date. So in your calendar and on your to-do list on Canvas, it should be showing up as due on Sunday. All right. So the next section is technically the mean value theorem, but we're just gonna skip the mean value theorem. So we're just gonna skip this section. It's not incredibly important, so we're gonna skip it. We're gonna go on to things that are a little bit more important and relevant to what we're doing. Not that mean value theorem isn't important. It is important, but I mean, it's not a calculus topic that you're going to miss if you don't cover it. So we're just not going to. So we're going to go straight into derivatives and graphical interpretations. We're getting into what I think is some of the fun stuff in calculus. I mean, there's a lot of fun stuff in calculus, but I think that graphs are a lot of fun when it comes to calculus. We're going to get into curve sketching in the next section, which is really, really fun. You get to draw graphs, and I know not everybody likes drawing graphs, but I'm hoping I can make it a little bit more fun than normal. But before we can draw graphs, we need to talk about how calculus relates to graphs. So we know about increasing and decreasing functions. This is something we talked about in Math 126. So like a function is increasing if you're going uphill, a function is decreasing if you're going downhill. So we've already talked about increasing and decreasing functions before in previous math classes. Something I want to mention is that for us, when we talk about increasing and decreasing intervals, we always use open intervals. This is not the same for all math teachers. This is not the same for all math textbooks. Different textbooks, different teachers have different preferences here, but for us, all increasing and decreasing intervals are going to be open intervals. And by an open interval, what I mean is that the interval would look something like 1, 3. This is an open interval. A closed interval would have brackets. So we're not using a closed interval, we're using open intervals. So when I say open, what I mean is that we are using parentheses on our intervals and not brackets. So, let's see, there we go. Looking at this graph right here. If we want to know where this graph is increasing, we are a little ant, we walk from left to right, and when the little ant is walking downhill, the function is decreasing. When he's walking uphill, he's increasing. So I think this is a highlighter right here. So right here, that is all decreasing because he would be walking downhill if you were a little ant. Here you'd be walking uphill. Then you'd be walking downhill. And here you're walking uphill. So the function is increasing on these red intervals where he's walking uphill. Oops. So this first interval right here is from -1 to 0. And then the next interval is going to go from 2 onward, assuming this graph goes off the page. Those are the x values. We talk about the x values. The function is decreasing on these 2 intervals. So the first one kind of like starts at -infinity and goes up until -1. So -infinity to -1. And the next interval starts at 0 and goes until 2. Something to mention, with increasing and decreasing intervals, we don't do union symbols. There's a real nuance there as to why we don't do the union symbols. It's not the end of the world. It's not something I'm going to mark down for, but it's something that's, I think, important to know. The reason that we don't use those union symbols here, the reason we use and, is if you use a union symbol, that means it's increasing the entire time. So that would mean that when you stopped at 0, if there were a union symbol, that would mean that the next y value that you jumped to would be greater than this y value. So you would have to have it so that it was always increasing, so that here at 2 when it started, that the y value was greater. But clearly the y value is not greater here at 2. It's actually less than where it was at 0, but it doesn't matter because it's increasing here. So we use and symbols because it's not increasing on this entire interval. It's not increasing on as if this were one interval, but each of these individually is increasing. Let's make that look a little better. So we don't use union symbols, we use and. This is an and, just in case you can't read my handwriting. This right here is a union symbol. So something to note, when the function is increasing, if we were to draw any tangent line, so if I draw a point right here and I draw a tangent line, or if I take a point right here and I draw a tangent line, the slopes of those tangent lines are positive, right? Let me kind of clarify here. A positive slope goes up like this. This is positive slope. A negative slope slopes down like this. This is negative slope. So on the increasing portions, anytime you would draw a tangent line, the tangent line would have a positive slope. Right? So when the function is increasing, the slopes of the tangent lines are positive. But when the function is decreasing, if you were to draw any of these tangent lines, any place that you draw a tangent line on a decreasing portion, those slopes are negative. The slopes of those tangent lines are negative. And I know this is a pretty messy picture here. The other thing to notice is at the places where there's a max or a min, so here there's a min, and we've talked about this before, the slopes of the tangent lines are 0 because they're horizontal. Now, technically, they don't have to be 0. We've also talked about situations where the graph is pointy. So we've talked about how the graph could be, pointy, and you could have no derivative, no tangent line at a max or a min. So that's another possibility, is that if you had a pointy graph, that the derivative doesn't exist at a max or a min. But if the graph is smooth, then the derivative, the slope of the tangent line at a max or min is going to be 0. Oh, and someone said it looks like a bunch of lightsabers. It does look like a bunch of lightsabers. I like that. This is my lightsaber picture. All right, so looking at this theorem. So if we have a differentiable function, if it's differentiable on an interval, if the derivative is greater than 0 on an interval, so if it is positive, is what this says. If it is positive on an interval, then the function is increasing. So if f prime is positive, the function is increasing. If f prime is negative, so less than 0, the function is decreasing. And if the derivative is equal to 0 on an interval, so if the derivative is 0 for an interval, the function is going to be constant on that interval. So this is the kind of association I want you to be making. F prime positive, that means increasing. F prime negative, that means decreasing. F prime 0, this is either going to be constant if you're on an interval, or it's going to be the top or bottom of a hill, or it's going to be a flat point. So the ways that this can happen, you could have literally just a part of the graph that was flat. That would be constant. For a flat point, what I mean is like you could have the top of a hill right here, it would be 0. The bottom of a valley, the derivative would be 0. And additionally, if you have something that looks like this, where it kind of like flattens out right here, that would also have the derivative be 0 there. All right. So let's use this information in a problem. So we want to find the intervals of increase and decrease for the following functions. So we have this function, x to the 4th over 4 minus 5 halves x squared plus 2. Your first step is going to be finding all the important values, not the critical values, like important values. You want all values. So you want to find f prime first, obviously, because you need that to find the important values. And all important values. Right? Something to note about this function here, the first part could be rewritten as 1/4 x to the 4th. You don't have to do quotient rule on x to the 4th over 4. In fact, you shouldn't do quotient rule on x to the 4th over 4. It would take a lot longer and there's no reason to do it. So f prime of x, 1/4 times 4 is just going to be 1, so this will be x cubed minus 5x. And the derivative of 2 is 0. This gets set equal to 0. Factoring out an x, then we have x squared minus 5 equal to 0. This doesn't look like a difference of squares, but it is kind of a difference of squares because you can do x plus the square root of 5, x minus the square root of 5. equal to 0. And we get x equal to 0, x equal to negative square root 5, and x equal to square root 5. So those are our important values. You might be wondering to yourself, well, why would we find important values? Why would that be something we want to do? We want to find where this thing is increasing and decreasing, and why would this be the first step? Well, my friends, going back to this picture here, this lovely lightsaber picture, what you'll notice is that the derivative is either 0 or non-existent at places where it changes from decreasing to increasing. Because really what we want to do, I'll bring this all back, but I'm just going to erase it for a second. Really what we want to do, we don't have the picture of this function, right? We don't know what the function we're working with looks like. But if we want to know where it's increasing and decreasing, what we really want to know is where does it change from increasing to decreasing or decreasing to increasing? Where are those changing points? Because if we can find out where it changes, then we can just figure out what's going on in the in-between. And the places where it changes are the places where the derivative is either 0 or, like in this case, non-existent. So if we can find the places where the derivative is 0, those are the possible places where it can change. It might not change because it's possible for that to happen, but those are the possible places where it can change. And then we can make a sign chart. That's going to be the next part. We can make a sign chart to find out if the derivative is negative or positive. I'll put my lightsaber picture back there. So our next step here, we've found the possible places where this graph might change from increasing to decreasing. So our next step, we're going to make a sign chart using those important values. Oops, let's see. So we have negative square root of 5. And if you plug that in your calculator, just so you have an idea of where it is, that's about negative 2.2. We have 0, and then we have positive square root of 5, which is approximately positive 2.2. We want to know those approximations so that we're able to find test values. So I want a number less than negative 2.2, so I'll use negative 3. Here I'm going to use negative 1, positive 1, and positive 3. And we are taking these values and we are plugging them back into, it doesn't matter if you want to use this guy or this guy. So if you're using this bottom one here, just treat square root of 5 as if it were 2.2. So negative 3 is negative, so when we plug it into the first one, we get negative. Negative 3 plus 2.2 would be a negative. Negative 3 minus 2.2 would be a negative. 3 negatives make a negative. Negative 1 plugged in here is a negative. Negative 1 plus 2.2 is positive. Negative 1 minus 2.2 is negative. 2 negatives make a positive. One plugged in here is positive. 1 plus 2.2 is positive. 1 minus 2.2 is negative. 1 negative makes a negative. And then plugging 3 in, 3 is positive. 3 plus 2.2 is positive. 3 minus 2.2 is positive. And 3 positives make a positive. This problem really should have had a bit more room. So now that you have that information, you actually have all the increasing and decreasing information. So you use the sign chart to determine the intervals of increase and decrease. So remembering what I had said before, these right here are representing this, like the derivative. This is representing whether the derivative is positive or negative. So if f prime is positive, that means that f is increasing, right? If the derivative is positive, the original is increasing. If the derivative is positive, the original is increasing. So f is increasing on these intervals where it is positive. And we're always going to do open intervals. So it's increasing on negative square root 5 to 0 and square root of 5 to infinity. If the derivative is negative, that means the original function is decreasing. So the original function is decreasing on these two intervals. So it's decreasing on negative infinity to negative square root 5 and 0 to square root 5. Can I answer questions on finding those intervals of increase and decrease? Okay. So let's try another one. For this guy, we have x squared minus x minus 3 ln x. So it's important to note that this original function has some domain restrictions because you can't plug in anything that's less than 0 to ln's. You also can't plug 0 in. So the domain of this ln x part restricts the domain of the entire function. And the domain is from 0 to infinity. And that's because we don't include 0 because 0, you can't plug 0 into ln, and then it has to be positive. So our first step, finding y prime. Finding y prime. So y prime is going to be equal to 2x minus 1 minus 3 times 1 over x is the derivative of ln x. I'm going to write this as 2x minus 1 minus 3 over x because that's the same thing. When finding important values, you're going to want to find places that make the numerator and denominator 0. Not at the same time necessarily, but places where the numerator is 0 and places where the denominator is 0. In order to do that, you're really going to need to make this into one fraction. So if you have one fraction in here, you need to combine it into a total of one fraction, simplify it all into one fraction. So I have 2x minus 1 minus 3 over x. To make this into one fraction, we can just set it equal to 0 if we want to. To make this into one fraction, you're going to need to make common denominators. Right? So the common denominator you can make is x. So you have 2x, and you can multiply him by x over x minus 1 times x over x minus 3 over x equal to 0. So you get 2x squared over x minus x over x minus 3 over x. They can be combined into one fraction, so 2x squared minus x minus 3 over x equals 0. This can be factored. So it factors into 2x minus 3 times x plus 1. I'll save you the time of factoring it. And then you're finding places that make the numerator 0 and the denominator 0. So really you're looking at all of these possible places. So x equals negative 1, x equals 0, and x equals 3 halves. Those are going to be your important values. Now, what's important here is that if we're looking at where they're increasing and decreasing, if we're looking at where it's increasing and decreasing, the function is only on its, we're only on 0 to infinity. So it's not like negative 1/2 or 0 is going to be important to us because the graph doesn't exist at negative 1. There's no graph until 0. It starts at 0. So we're going to take out ones that aren't in the domain, which does make them critical values, but we're taking out these guys because they're not in the domain. Now, the reason that we aren't going to call these critical, we're not looking for critical values, is because that there are times where things aren't in the domain that we are interested in them. So for instance, in the case where you have like a graph that has asymptotes, even though this value right here wouldn't be in the domain, a function can go from increasing to decreasing at this point right here. So you would care about this value even though it's not in the domain because it can change there. But because our graph just doesn't exist prior to 0, negative 1 doesn't make sense. It's not like negative 1 is an asymptote. It's just that the graph doesn't exist prior to that point. So we're going to make ourselves a sign chart. Our graph starts at 0 because ln x, right, restricted our domain. And we have 3 halves. We'll take some test values. So I'll use 1 and I will use 2. And you're plugging into this guy right down here, right down here. So if you plug 1 into 2x minus 3, you'll get 2 minus 3, which is negative. 1 plus 1 is positive. And then if you plug 1 into the denominator, you'll have a positive. So a negative times one negative is going to make it negative. I'll just put that negative up here. For 2, 2x minus 3 is going to be positive because it'll be 4 minus 3, so positive. 4 plus 1, or 2 plus 1 is positive, and 2 itself is positive. 3 positives make a positive. So this function is increasing where the derivative is positive, so it's increasing from 3/2 to infinity, and it is decreasing from 0 to 3/2. So that is where the derivative is negative. So derivative is negative means it's decreasing. Derivative positive means it's increasing. Can I answer questions about that? I'm going to go find a problem for us to practice real quick. Sorry, I'm looking for one that's going to be I want one that's going to have answers that work out. All right, this is going to have a tiny bit of factoring, but this one should be fine. All right, so I'm going to give you one to try. Okay, so I'm going to go ahead and give you, I'm going to give you 4 minutes to work on this one. So I'm going to stop it and put on a 4-minute timer. All right. So hopefully you've been able to get some progress through this problem. Your first step should be taking the derivative. So you'd get 120t squared minus 20t cubed minus 20t to the 4th. You can factor out a 20t squared from everything. You'll get 6 minus t minus t squared. I'm going to, because I want to rearrange this and have the leading term be positive, I am going to factor out a negative. So negative 20t squared, which would give me negative 6 plus t squared. And then I can rearrange it in the order I'm used to for factoring. T squared plus t minus 6. That factors into t plus 3 times t minus 2. So we get t equal to 0, t equal to negative 3, and t equal to 2. Making ourselves a sign chart. Negative 3, 0, and 2. just choosing some test points. And then I'm plugging it into here. Something to keep in mind, this very beginning thing is negative. So there's really like, if I just kind of circle this, there's a negative in front of all of these because that negative 20 out front is negative. Keep that in mind. Then plugging into t squared, that one's always going to be positive, right? Negative 4 squared is positive. Negative 4 plus 3 is negative. Negative 4 minus 2 is negative. 3 negatives make a negative. And you can put that up here if you want to. Negative 1 squared is positive. Negative 1 plus 3 is positive. Negative 1 minus 2 is negative. 2 negatives make a positive. 1 squared is positive. 1 plus 3 is positive. 1 minus 2 is negative. 2 negatives make a positive. 3 squared is positive. 3 plus 3 is positive. 3 minus 2 is positive. 1 negative makes a negative. So our intervals of increase. So you can split this one up. However, since this one is continuous there at 0, sometimes they have to be split up if there's like continuity issues here. If there were like a domain issue, you would have to split this up. Because 0 is in the domain of this guy, I'm just going to take this entire interval from negative 3 to 2. And the function is decreasing on negative infinity to negative 3 and 2 to infinity. Can I answer any questions about that? Okay. So, like I said, this is all leading up to us talking about drawing our own graphs of functions. So we start talking about increasing, decreasing. We talked about how like the derivative would be 0 or non-existent, where there's a max or a min. But we can actually tell based upon this chart right here, I could actually tell you which of these are maxes and which of these are mins. I can tell you that this is going to be a minimum. This is going to be neither. And this is going to be a maximum. I can tell you that. Just by looking at that chart, I can tell you that. I haven't looked at the shape of this function, but if I graphed it on a graphing calculator right now, you would find that I am right. So how did I do that nifty magic trick there? Well, if you have a derivative that changes from positive to negative, right? So positive to negative would be increasing to decreasing. If it goes from increasing to decreasing, you have a maximum. You have a relative max. If your derivative changes from negative to positive, so if your function goes from decreasing to increasing, that means that you have a relative min. And if f prime doesn't change signs at c, then nothing interesting happens. So if it goes from like increasing to increasing, that would be a picture like this. Or if it goes from decreasing to decreasing, so that would be a picture like this. Nothing interesting happens. There's no maxes or min that's there. So when I look back at this chart right here, here's what I'm doing in my head. All right, decreasing, increasing, increasing, decreasing. So if I kind of follow this picture in my head, decreasing, increasing, minimum. Nothing interesting happens here because it doesn't change sign. Increasing, decreasing, maximum. So that's how I was able to say minimum, maximum, nothing. I don't encourage you trying to memorize this as if it were like a flashcard, like positive to negative, relative max, negative to positive, relative min. That's not useful. What's useful is conceptually thinking about what it means. Being able to draw this picture, I don't in my head think about the words here. I think, okay, it has a max. If it has a max, I draw myself a picture of a max. Increasing, decreasing. If it's increasing, the derivative is positive. If it's decreasing, the derivative is negative. So I work it backwards. I don't have it as a memorized fact in my head, right? I don't have it memorized like you would memorize a flashcard type test, like terminology. I have it as a concept of understanding what the function is doing and what the derivative means, what that picture would look like, if that makes sense. So now what we're going to do, and this is going to be kind of common from here on out, is we're going to find intervals of increase, decrease, and we're going to find relative maxes and relative mins. So with this function, I'm going to rewrite it for us. This is the same thing as 1/4 x to the 4th plus 1/3 x cubed minus 8x squared minus 16x minus 5. We're going to take the derivative. We're going to find our important values. We're going to make a sign chart, and then we're going to determine which ones are maxes and which ones are mins. So my derivative is going to be x cubed plus x squared minus 16x minus 16, setting it equal to 0. This is going to be a factoring by grouping situation. From the first group, I can factor out an x squared, and I'll have x plus 1. From the second group, I can factor out a negative 16, also left with x plus 1. I can factor out the x plus 1, and then I have an x squared minus 16, which is a difference of squares. So the important values are -1, -4, and 4. I make a sign chart. -4, -1, 4. I choose my test values. You can choose any test values, by the way, inside that interval. So if you wanted to choose -20 right here, or if you wanted to use -3, or -3.5 if you wanted to be wild, that's totally fine. You can choose whatever values make your heart most happy. So I'm plugging these test values back into this derivative. Right? So -5 plus 1 is negative. -5 plus 4 is negative. -5 minus 4 is negative. 3 negatives are going to make a negative. -2 plus 1 is negative. -2 plus 4 is positive. -2 minus 4 is negative. 2 negatives make a positive. Zero plus 1 is positive. 0 plus 4, positive. 0 minus 4 is negative. 1 negative makes a negative. 5 plus 1 is positive. 5 plus 4 is positive. 5 minus 4 is positive. and I get a positive. Once again, all I've done for each of these is plug each of these values into this factored form right here. And now I'm just going to draw myself a picture. So negative is decreasing, positive is increasing. So decreasing, increasing, decreasing, increasing. And then, just kind of connect the dots if you want to. Right? You can tell that's a minimum, a maximum, a minimum. So we are increasing on the places where it's positive. So from -4 to -1, and from 4 to infinity. We are decreasing from -infinity to -5, and from -1 to +4. There's a relative min at x equals -4 and at x equals +4, right here and right here, and a relative max at -1. So it's kind of fun. I don't have a great idea of what this graph looks like, but I have a decent one, right? I know it's not going to look exactly like this, but I know what it's going to kind of be shaped like. And that's useful. Right? So let's look at another example. We're going to look at x plus 3 over x squared. Something I want to note right away. This is a rational function. And we know things about rational functions about the way that they're shaped. What happens at the places where the denominator is 0? Can someone tell me what happens at the x values where the denominator is 0? In a rational function, what happens? Yeah, there's an asymptote, right. So there are vertical asymptotes when the denominator equals 0. So if you have an asymptote, is it possible to have a max or a min there? Is that a possibility? Right? If I just draw a random graph, I am literally just drawing a random graph right now. But let's say this graph does something like this. Is it possible right here to have a max or a min if there's an asymptote there? No, right? This x value is not even in the domain. So you can't have any extrema at these asymptotes. You can't have extrema at values that are outside the domain. You may change from increasing to decreasing there, but you cannot have any maxes or mins there. And I'll show you how I take care of that. So we're going to do this the same way we've done everything. We're going to take the derivative. This is quotient rule, right? So the numerator, f, the denominator is g. So f prime is 1, g is x squared, minus g prime is 2x, times f is x plus 3, all over g squared, so x squared squared. So simplifying, we have x squared minus 2x squared minus 6x, all over x to the 4th. That's going to be negative x squared minus 6x over x to the 4th. You can factor a negative x out on top. So you'd have negative x plus 6, all over x to the 4th. And if you wanted to at this point, you could cancel one of these x's out, so that you have negative x plus 6 all over x cubed. So our important values here are negative 6 and 0. However, when I draw my sign chart, I'm going to be careful. So when I'm looking at problems like this, oops, where did my 0 go? When I'm looking at problems like this, I am careful because I know in this original that there is a vertical asymptote at 0. I know this. I know there's a vertical asymptote at 0 because the denominator is 0 when x is equal to 0. So I make note of that at the very beginning of the problem, right? I'm going to make note that there's a vertical asymptote at x equals 0. And I am going to draw a very different type of line here at 0, so that I make note to myself that there is a difference. I'm going to put negative 6 as normal, but 0 is different, not because it makes the denominator 0. That's not the issue. The issue is that it makes the original function 0 in the denominator. Because that happens, I have to make sure I make note of it on my chart so that I don't include it as a max or a min. You need to do something to let yourself know that, remember, we're not including 0 as a max or min because there's an asymptote there. So I'll choose some test values. And I'm plugging them into this function, keeping in mind there is a negative out here. So these are all going to be fractions, but because of this negative right here, these are all going to have a negative in front of them. Negative 7 plus 6 is negative. Negative 7 cubed is negative. 3 negatives make a negative. Negative 1 plus 6 is positive. Negative 1 cubed is negative. 2 negatives make a positive. One plus 6 is positive. 1 cubed is positive. 1 negative makes a negative. So we are decreasing, increasing, decreasing. Kind of drawing in our little graph here, right? Decreasing, increasing, and then asymptote, and then decreasing, and asymptote up here. So while there is a minimum here at negative 6, there's no maximum here because this is an asymptote, and you can't have a max or a min at an asymptote. However, it was really important that we included, so 0, because 0 is not in the domain, 0 is not a critical value. So the reason that we say important values here and not critical values is because you need to know about this important value, even though there can't be a max or a min there. If you just said, oh, I don't care about 0 because it's not in the domain, your sign chart would be all messed up, right? Because you wouldn't have this marker here. And depending on what test value you chose, you would only get one increase, or you'd either have increasing or decreasing, but really it's increasing here, decreasing here. So it's really important that you included 0 on your sign chart because it does change from increasing to decreasing. So we are increasing from -6 to 0. We are decreasing from -infinity to -6 and 0 to infinity. There's a relative min at x equals -6, and there's no relative max. Can I answer any questions on that example there? So if the asymptote was the other way, then there would be no min. Right. So are you asking like if the asymptote was here at -6 instead of being at 0? If it opened down instead of up. Oh, so like, yeah. So like if your picture of your graph, if it was like, let's see. So like if it were instead, if the graph looked like this, something like that. Right, then there would be no relative min. There would be a relative max right here, but no relative min. Yes. Excellent question. All right. So we're going to do the same thing for this next one. Okay. We are going to have to do product rule to take this derivative. And there's also going to be some chain rule in here. So we're taking a derivative. Okay. So product rule is f prime g plus g prime f. F prime is going to be 2 z minus 1 raised to the first power, and then the derivative of the inside is 1. So I don't really need to write any of that. I'm going to erase it because raised to the first power is just itself. So that's f prime times g, which is z plus 3, plus g prime, which is 1, times f, which is z minus 1 quantity squared. So if I clean this up a tiny bit, you'll notice that both of these have a z minus 1 in common, and I can factor the z minus 1 out. If I factor it out, what's left over here is 2z plus 3. And there would be 1z minus 1 left over here. This is just being tricky with our factoring. So factoring out a z minus 1, you're left with 2z plus 3. Over here, if you took out one of the z minus 1s, you'd still have a z minus 1 left. And you don't have to do this way. You could absolutely FOIL this whole thing out. That would also work if you really wanted to do that. You'd have, let's see, 2z squared. Let's see, so plus 4z minus 6 plus z squared minus 2z plus 1. So you could combine those all together and you'd get 3z squared plus 2z minus 5, and you could factor it from there. That totally works as well. But if you want to be tricky about it, you can do it this way. So you have 2z plus 6 plus z minus 1. This factors into 3z plus 5. So we have z minus 1 times 3z plus 5, which is what this would factor into. So if you took this and you actually just FOILed it, you would get z minus 1 times 3z plus 5. And this is the derivative. So our important values are z equal to 1 and z equal to negative 5/3. So negative 5/3, 1. Let's see, we have z equals, that would, negative 2 will work. Zero and positive 2. So negative 2 minus 1 is negative. Negative 6 plus 5 is negative. Two negatives make a positive. 0 minus 1 is negative. 0 plus 5 is positive. So that'll be negative. 2 minus 1 is positive. 6 plus 5 is positive. Two positives make a positive. So we have increasing, decreasing, increasing. So you draw yourself a little picture. We don't have to worry about any, you don't need to worry about domain issues here because this was just a polynomial. So we are increasing from negative infinity to negative 5/3 and 1 to infinity. We are decreasing from negative 5/3 to 1. We have a relative max at z equals negative 5/3. And we have a relative min at z equals 1. And you could also say x equals, because technically, like, they are x values. So you could say x equals negative 5/3 and x equals 1. That would be fine. All right. All right. This one's more of a tricky one. So here's what's going on here. We are given a graph of G. We want to graph G prime. So this graph we're going to draw is the graph of G prime of X. So this gets a little bit tricky. Here are some things we know, and it kind of helps to start with the things we know. We know here that the derivative is going to be 0, right? We know at -2 that g prime is 0. We know that same thing happens right here. G prime of 4 is 0. And down here, g prime of 6 is 0. Right, so I'm making this graph here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2. I know that g prime of -2 is 0. So when I'm graphing g prime, I know that the y value is 0 at -2, it's 0 at 4, and it's 0 at 6. So I can graph those points. The next thing we know, what color did I use for decreasing? I used blue. The next thing we know is that we are decreasing in these locations. If g is decreasing, that means that g prime is negative. When a function is negative, that means it's below the x-axis. Right? So this location down here is where g prime is negative because it's below the x-axis. And then the same thing can be said for when g prime is positive. If g prime is positive, then its graph will be above the x-axis. Once again, this is the graph of g prime, not the graph of g. We have the graph of g. So increasing. So if g is increasing, g prime is positive, which is above the x-axis. The other thing that we already wrote down here is that where the derivative is 0, so at the maxes or mins, there's an x-intercept, right? Because that's where there's an x-intercept on g prime's graph, because that's where g prime is 0. So then for the rest of this, it's just kind of, guessing as good as we can. You can only really do so much here. You can tell that the slopes of these tangent lines are going to get kind of shallow. So this has a pretty slow slope. This is almost like a constant function. It's like flattening off here. So g prime is going to get kind of closer and closer to 0. It's going to kind of make this type of shape because the derivative is getting closer to 0 because it's flattening. For the rest of the graph, I mean, you know, this thing starts off kind of shallow, but then it gets pretty steep and then it gets less steep. So you know, you could just do one of these because it's less steep and then more steep. And then it's just going to get more and more steep. Obviously, you can't make a perfect graph. The more important thing on this is not the shapes that are made right here and right here. What's more important is where it's positive, where it's negative, and where the x-intercepts are. Those are the important parts of that graph. Okay. All right. So let's bring in the next portion of it. The next portion of this is concavity. Concavity is probably a word you've heard, and it kind of means the same thing as it does in like regular plain old English. But when you say concave, you don't typically say concave up or down when you're talking about the word concave in English. So let's talk about the up and down part. So graphs have another characteristic, and it's called concavity. Concavity just means either it's making a happy face, and we call this concave up, or it makes a sad face, which we call concave down. So for concave up, that would be like this portion right here, because it's a happy face. So this part right here, this is concave up. This portion right here of the graph, we would call concave down because it is a sad face. So this is the graph of f. This is the graph of f prime of this same function. So something to notice, the places where we are concave down are the same places where f prime is negative. Right? So when f is concave down, f prime is not negative, decreasing. F prime is decreasing. When the graph is concave up, the derivative is increasing. So here's kind of the connection that gets drawn. if, let's see, it's the best way of drawing this. Like, if f is concave up, that means f prime is increasing. And we know when a function is increasing, that means its derivative, in this case f double prime, has to be positive. Right? If a function is increasing, that means its derivative is positive there. If your original function is concave down, then your derivative is decreasing. And if a function is decreasing, then its derivative, in this case f double prime, is negative. Right? So if f prime is positive, that means f is increasing. So it's increasing. If f prime is negative, that means f is decreasing. On the other hand, if f double prime is positive, that means f is concave up. Concave up is this way. If f double prime is negative, that means f is concave down. All right, here's how I remember this. The positives and negatives kind of make a lot of sense. If we're increasing, decreasing, right? So like f prime positive and increasing makes sense. Negative and decreasing makes sense. For concave up and concave down, the way I have it memorized is that positive people are happy people, so they make the happy face. And negative people are down, so they make the sad face. They're down all the time. So f double prime negative is concave down, that is the sad face. F double prime positive is concave up, it is a happy face. The other thing to note, and it's mentioned somewhere up here, right here, inflection points, places where we change concavity, so where we change from concave up to concave down, those are known as inflection points. So this right here is an inflection point. It is the point where f changes concavity. It changes from concave down to concave up. Okay. So here we go. Here's saying exactly what I've already said. If f double prime is positive, then f is concave up. If f double prime is negative, then f is concave down. Then we have an inflection point. An inflection point, if two things happen. One, you need f of a to exist, so you have to exist at that point. You can't have an asymptote. It has to, like, the x value has to be in the domain. And f changes concavity at x equals a. So you have to change from concave up to concave down or concave down to concave up. So your requirements here are 1, x equals A in domain of original function and B, F changes concavity at A. Those are the requirements to have an inflection point. So we'll do this problem. We're going to find intervals of concavity. So we're going to find intervals where F is concave up, intervals where F is concave down, and we're going to find the location of any inflection points. This is a very similar process to the one we did for increasing, decreasing. So instead of finding F prime, we want to find F double prime. So for F prime, this would be 4/3 x cubed minus 9x plus 7. F double prime, taking that derivative, would be 4x squared minus 9. Then we want to find any important values for F double prime. So we'll set F double prime equal to 0. This is a difference of squares, 2x plus 3, 2x minus 3. Get x equal to negative 3/2 and x equal to 3/2. Then we make a sign chart for F double prime. Making a sign chart, and we are plugging in to this function here. So negative 4 plus 3 is negative, negative 4 minus 3 is negative, 2 negatives make a positive. 0 plus 3 is positive, 0 minus 3 is negative, so this will be negative. 4 plus 3 is positive, 4 minus 3 is positive, 2 positives make a positive. Now it's important, we're looking at F double prime here. F double prime. So F double prime being positive means that, maybe it'd be better to put it down here, F double prime. F double prime being positive means that the original function F is concave up. If F double prime is negative, the original function F is concave down. If F double prime is positive, F is concave up. Notice that concavity changes at both negative 3/2 and 3/2, so those are going to be inflection points. You'll have to excuse me. Archie, can you no, that's not going to work. My husband started cooking, and so now my dog with the cone on wants out, and he can't open the door. Hold on just 1 second. Okay. I think he went outside, but Okay, there they go. funny because my puppy came in, and I was like, oh, maybe he'll open the door enough so that Toby can get out. But he did not open the door big enough for Toby to get out. So anyway, dogs. So the last step here is to state your findings. So in our case, concave up, we are concave up on negative infinity to negative 3/2, right? Concave up. And also on 3/2 to infinity. And then we are concave down, where right in here, where f prime, double prime is negative. So from negative 3/2 to 3/2. And then there are two inflection points. There's an inflection point at x equals negative 3/2 and also at 3/2. Right? Questions on that one at all? So to reiterate, this is the same process as finding increasing, decreasing. It's just that you find the second derivative instead of finding the first derivative. So I'm going to give you guys one to practice. So here we're finding concavity, and then you're also going to find inflection points. So this is g equals x to the fourth minus 12x cubed plus 84x plus 4. With these ones, you can imagine I can't just make these ones up off the top of my head like I could with derivatives, because these ones you need it so that the second derivative factors, or at least something interesting happens with the second derivative. So you can't just kind of throw numbers out there or things go really bad. So anyways, I'm going to give you guys 4 minutes to do this one. So find concavity intervals and inflection points. Right. Oops. Not sure what happened there. Let's see. So with this problem, we'll find our first derivative. Then we'll find our second derivative. Setting that equal to 0. We can factor out a 12x. So we get x equals 0 and x equals 6. Find some test points. So we'll have negative, negative, that makes a positive. Positive, negative makes a negative. Positive, positive makes a positive. So we have concave up, concave down, concave up. So our concave up from negative infinity to 0, and from 6 to infinity. Concave down from 0 to 6, and we have inflection points at 0 and 6. Because concavity changes at both places. Any questions on that example? Okay. This part, so someone in the chat said, you should make the entire homework like this because I like this part. I think this part is fun. I think if you like this part, like you're gonna like the curve sketching stuff. It gets really fun. It's like it's very puzzly. I know related rates is also kind of puzzly, and not everyone likes related rates, but this stuff is a lot more like there's a method to it. This is how you do it. This is the algorithm, and you're gonna get to the right answer as long as you follow this algorithm. So I'm glad that you're liking this material. All right, so for the next, I'm going to skip these two examples. They're not my favorite examples. I'm just going to skip them because I want to talk about the second derivative test before we finish up here today. So the second derivative test says, hey, hold on just a second. I think I hear my husband yelling at me. Hold on. He's talking on the phone. All right, so the second derivative test says, hey, I know that like you've been doing this thing to find maxes and mins where you make a sign chart and do all that fun stuff, and that's cool. You can totally do that. You can make a sign chart to find maxes and mins, but we know with concavity, the shape of the graph at that point. So like if I knew that the derivative was 0 somewhere, and I knew the concavity at that area, I could tell if it was a max or min, right? If the derivative is 0 and I'm concave down, then it's a max. If the derivative is 0 and I'm concave up, then the that is going to be a min. So if f double prime is greater than 0, so if you are concave up and you have that f prime is 0, so f prime is 0 and f double prime is positive, so you're concave up, you have a relative min. If f double prime is negative, so that means you're concave down, and your derivative is 0, that means you have a relative max. Finally, another thing could happen, and you could have the f double prime was 0, f prime is 0, f double prime is 0, and at that point anything could happen. The test fails. You can't use the second derivative test there. Right. So this part down here is just explaining what I've already explained here. So if f prime is 0, that means you have a horizontal tangent line. If f double prime is positive, that means that f is concave up. Which means you have a local or relative. Relative and local mean the same thing. Local min. Right? This is what I've already said, but I'm just going to write it again. If f double prime is negative, that means f is concave down. So that would be a local max. So this is useful in certain situations and completely not useful in others because sometimes finding the second derivative is not easy. But in the cases where it is easy, like in the cases of, I don't know, polynomials, it's really nice. So we can find local extrema using the second derivative test here. We have our function here. So we're going to do the first derivative and find the critical values. So f prime here would be 6x squared minus 6x minus 12. I can factor out a 6, and I have x squared minus x minus 2. So I have x minus 2 times x plus 1 equal to 0. X equal to 2, x equal to negative 1. Those are my critical values. Now, normally, if I were doing the first derivative test, which is making the sign chart, if I were I would make a sign chart now, and that's fine. It doesn't take too long to do. But if I'm doing the second derivative test, I find f double prime, and then I plug the critical values into f double prime. So f double prime, and trick here, go back to the first one, go back to the first guy right here, and take his derivative. So f double prime will be 12x minus 6. So we plug in the critical values. F double prime of 2, that's 12 times 2 minus 6, 24 minus 6, that's 18. F double prime of negative 1, that's 12 times negative 1 minus 6, that's negative 18. So if f double prime is positive, that means you are concave up, which is this shape. Happy people are concave up, so you have a min. If f double prime is negative, if f double, come on here. If f double prime is negative, that means you're concave down, so you have a max. So at this point, what you can say is that there is a relative max, right, at negative 1. And there's a relative min at x equals 2, because that's where it was concave up. So in some cases it's faster, in some cases it's not, but it is something you can do. The second derivative test is something that you can choose to do to find maxes and mins, or determine whether your critical values are maxes of mins. Right? So there's another problem on this, but I'm not going to do that one right now. I can always do that one on Monday. I am going to post homework problems for this section soon. Someone asked the question, this is a great question, is there an easy way to tell if the test or the sign chart would be faster? In general, if it's a polynomial, it'll probably be faster to do the second derivative test. If it's not a polynomial, it probably will not be faster. So if you notice that you're going to have to do like chain rule or quotient rule or product rule, that would be a situation where I would say probably not as fast. But with a lot of polynomials, if it's not going to be like a really gross polynomial, it'll probably be faster to plug it in to the second derivative. So basically polynomials are the answer there. Polynomials make it easy. Yeah, no problem. Are there any other questions? Okay, so like I said, the exam again is due on Sunday now. I have moved that due date back to Sunday, so you have until Sunday to work on it. Make sure you turn it in by Sunday night at 11:59 p.m. Please make sure all the pages are there. So double check, make sure that every page is included when you turn it in. The exam review, the entire thing is uploaded. If you go to the exam review page on the from the front page of Canvas and click on exam reviews, there's 2 links. So there's one for part 1 and one for part 2 of the solutions for the exam 2 review. So I thought I'd mention that. All right, that's everything I have for you. Have a fantastic weekend and rest of your week. And if you have questions, just feel free to email me.